This is the only video you need to master RAG in N8N. It will take you from a complete beginner, even if you have no idea what RAG means right now, to a RAG master step by step. So whether you're a business owner trying to implement AI within your own business, or someone who wants to sell AI and automations to other businesses, this is the video I wish I had access to when I first started my automation and AI journey just shy of a year ago now. When I started looking into RAG, I got overwhelmed very, very quickly. There was so much stuff out there, but most of it was a little bit overcomplicated, but also missing the detail to make it actually useful on my client builds where we could build a high quality end product. And only after making hundreds of workflows within N8N, getting a top rated Upwork profile for selling AI agents and automation to other businesses, was when I really got to see how powerful RAG could be and how to make it actually useful in a business environment. So I made this video to help you build a RAG agent for your own use case. So this will be applicable to your own use case, save you a lot of time and headaches that I went through when learning, and share with you exactly what works. But don't worry if you don't know what RAG means yet, because we'll be starting from scratch and we're talking exactly through what is RAG, when and why you'd use it over the alternatives, what the limitations are, and actually how to build in a process to get past those inside N8N. We'll be talking about enhancements to RAG, but also some of the alternatives there. And by the end of it, if you stick around, you'll have 4 RAG agents that you can implement right away in your own or your client's businesses. And by the way, if you want to speed up the process and build along side by side, then all of these templates are available in my paid school community, which is linked down below in the description. All you need to do is head into school.com/scrapes, head to the classroom. Inside the plug and play template library, we've got the complete RAG masterclass, full with prompts, the queries, everything you need to get this set up really quickly. You're going to come down here. We've got all the downloadable files. We've also got the downloadable N8N workflow. And then you're going to go into N8N, hit create workflow, and you're going to import that directly from the file you just downloaded. What that's going to do is load up all of the workflows we're going to build in here so you can see them side by side as you build them out, or just plug and play directly so you can test them out straight away. And it comes full with all of the different images we discussed, the queries, the prompts, etc. Now let's jump into what RAG actually is. So RAG stands for Retrieval Augmented Generation. And let's split that up first into 2 separate phrases. We've got the generation. So you're probably familiar with using something like ChatGPT. And when you prompt ChatGPT for an answer, you're hoping that it can retrieve the correct information from its data sources and provide that back for you. So that's the generation part. However, as you've probably figured, when you start to prompt ChatGPT, often that information is completely out of date. The training data only goes up to June 2024, for example, for GPT. And it also has no access to source data. So it might have been trained on some general data, but it doesn't have access to your business data. So those are 2 fundamental limitations of the generation part, which RAG aims to solve. So the retrieval augmented part, or the RA in RAG, is how do we augment your LLM prompt with that business information and basically say, okay, based on the question asked, this is the most relevant information. We'll throw that into the prompt so that the generation LLM or the underlying part answering the question has access to the right context. So this is what we're basically trying to do. We're giving the LLM some context in which to answer the question with its knowledge. Now, you might be thinking at this point, then why don't we just feed the context into the data every single time? That is absolutely an option. But RAG came about because when the first LLM or most popular LLM models came about, like GPT 3.5, the token limit of 4,096 tokens, which is roughly equivalent to 3,000 words, was not large enough to feed in vast amounts of context. Plus, a lot of the models that we tend to use nowadays have got significantly more expensive. So if you want a good writing style, you might be looking at Claude 3.5 Sonnet, but actually you're paying $3 per million input tokens. And if you're feeding in all your business documents and data, that can get very expensive. So RAG aims to solve that by effectively feeding in the data little by little. So RAG here displayed in the diagram is set up in two kind of phases. The first is ingestion and the second is retrieval. So when we have large business documents, what we're trying to do is put them into some sort of data store where we can pull little by little the most relevant information and add that back to our prompt. So in the ingestion stage, we're taking our large business documents, say a ton of PDFs that you use inside your business, financial documents, anything like that, and we are splitting that into chunks. So this is a process we call chunking, split it into individual documents. We then need to store it in some sort of database where we can retrieve it. So we split it into those documents, and then we store it in what we call a vector database through an embedding model. So let me explain exactly what that means. A vector database is where we represent words as points in a three-dimensional space. So you can see on the right-hand side, we have banana and pear. They're represented as points or vectors in that space, and they would be located in a close proximity because they actually have a similar meaning. So these vector representations decide based on the word semantics, how close should they be. So banana and pear may be close on this vector representation, but Apple phone, despite containing the word apple, is actually going to be far apart from the banana and pear. We break these words down into vectors using what's called an embedding model. And you can see as an example of man and woman here, we break them down into individual vector dimensions, and we end up getting a vector representation of a specific word. So this could be banana and pear, and they'd end up having a similar word there. What that means in the next phase, which is retrieval, is that for every query that we ask the database, we've also got to translate that query into a vector, i.e. send it through the embedding model as well, the same embedding model, so that we can find the most similar chunks that we've put in the database and bring those back. So for example, if I'm asking about the annual growth rate from some financial documents, those would be split into chunks. They'd be embedded in the database. And then when I'm asking about that, I might use slightly different wording, but the embedding or the vector representation would be similar because it's based on semantic meaning. That would go and retrieve the closest 5, 10, 15, or whatever we specify chunks from the database, bring it back and add it to our context. So what this essentially means is we're just adding the most relevant data into our prompt. So let's jump into making our first RAG. And I've opened up the N8N environment here. And if you're not familiar with N8N, then check out the full 4-hour masterclass that I've done that takes you from complete beginner through to an N8N intermediate level. But assuming you're familiar with N8N, we've opened up a new workflow and we've got our image in here of the RAG stages. So we've got the ingestion and we've got the retrieval. So we're going to build out step by step each of these stages, and we're going to show you which tools to use at which stage, what bits are important, but most importantly, when you're using it for your own business data, which I'd recommend whilst you follow this video, use your own business data, not the examples that I use. You're going to see some of the limitations of standard RAG demos. And in this video, we're going to cover exactly how to get past those limitations. And some of those will be around not giving enough context when you're splitting it into chunks. Others will be around updated data and how to make sure that your data is continuously updated and you're pulling the right information. And we've got a few other limitations that we're going to cover as well. So let's move on to the ingestion phase. So we've got our large documents. And for this first example, we're we're going to use some publicly available data. So we've got the Netflix investors page up here, and we've got the 2024 annual report, 2023 annual report. So multiple years of annual reports. So we're just going to download one as our first example of data we're going to upload. So I'm going to save that. I'm going to come back to the workflow. I'm just going to click the plus icon here. And what we'll do is we'll just start with the manual trigger. And we know that we've got to split these large documents into chunks. So first, we're going to need to get the document. So as an example, we can retrieve this from Google Drive. So I'm just going to go and create any folder in my Google Drive. And inside that, I'm going to upload the Netflix file. And then I'm going to take the link of the document. I'm going to make sure it's shareable. So anyone with this link can access this as a viewer. I'm going to copy that link. I'll go back to our workflow. And the first thing we're going to do is search for a Google Drive node. And what we're going to just do is hit the download file function. I've already connected to my Google Drive here. But if you've not previously connected to your Google Drive, I cover that in the 4-hour masterclass as well. Or I've got a separate tutorial on how to connect your Google credentials that you can check out. So we can either go from lists, so we've got all of our files listed, or here we just grabbed the URL. So let's put in the URL of the specific file, and we will cover later how to load in files as they're put into a certain folder. For now, we'll just do a demonstration with one Google Drive file, and we'll call this download file. So let's first test this step, and it's always important to test as you go along. Great, it's downloaded the file. We've got this as an output here as binary data, so we know that we're accessing the file correctly. If we go back to the diagram here, we've got our large document. We now need to split it into chunks. And if you remember, we've got to do that by using an embedding model to turn our document into data and then in turn into vectors. So right now this is a binary file, so we haven't actually extracted any of the text from the file here. So let's click on the plus icon first, and we'll go to Advanced AI. And it's not in the initial list here, it's down here in Other AI Nodes, and down here in Vector Stores. And at this point, we've got to choose which vector store we want to work with. So my preference is Supabase. So Supabase is free to use, and you're also able to store metadata or information about your data, a bit more context, so that we can retrieve it. Another popular alternative is Pinecone, but I find it a bit easier to load in, but harder to retrieve the correct information. So let's go with Supabase Vector Store. And in the actions here, we've got add documents to Vector Store. We've got retrieve documents, but obviously what we're doing is we're adding documents here to the Vector Store. So inside the Supabase Vector Store, we're just going to go to Docs up here. And this is to set up our project. So we'll go to Quick Start for setting up your Vector Store. And you'll see that this has an SQL command. You don't need to worry about this too much, but basically we're going to need to copy this. We're going to need to go into Supabase. You're going to need to sign up for an account for Supabase, confirm your account, and create a new project. So we're just going to create a new project here as an example, N8N demo. We'll give it a password. You'll need this password later, so make sure you store it somewhere. And that's going to spin up the project. It may take a few minutes to spin up that project. But in the meanwhile, we're going to go and set up the credentials that we need. So we're going to copy these credentials here. We're going to go back to our RAG agent. We're going to come up here and click Create New Credential. You can see we need two things. We need a host. So we've copied that URL there, and you can see that that's in a similar format. And we need the service role secret. So if we come back into Supabase, we're going to go down to project settings, and then we're going to go to data API to get back to this screen if it's taking you off. And then the secret that we need to take back is this service role secret here. So you're going to click reveal, and then you're going to come back to N8N and paste that service role secret in there. We're just going to save that, and I'll change the name of this to Supabase demo. And you can see that it's now gone green. It's connected successfully to our Supabase account. Now we need to create the tables in Supabase, our database, to enable us to load data in. So again, this is why we went to the docs, the quick start for setting up your vector database. And this is where we need the SQL command. Copy that. We're going to go back into our SQL editor up here. And all this allows us to do is copy paste in this SQL command. And all this is doing is creating tables that's able to receive our vector data that we're going to embed and send. So to put it simply, the documents that we are splitting up into chunks, they need to go into some tables. We're just setting up with this SQL command or SQL command, the ability to receive the documents in certain format. So we're going to run that down here. That's going to run and it's going to appear success, no rows returned. And if we go to the table editor, we'll see that it's now set up a documents table with ID, content, metadata, and embedding. And that is the vector database set up, just ready to receive our documents. So if we go back to our N8N environment, and now if you reload, refresh up here, you should be able to see two tables in here, documents and RPC match documents. So we're going to load them into documents and we're going to leave the embedding batch size as 200. And this is just the number of documents we're sending in a single batch. And all we're going to do here is come out into our dashboard and you can see that there's two things that we need to add here. The first is our embeddings model. So to remind you, our embeddings model is what splits up the data we load in or the question we ask into vectors. So the embedding model just works out the semantic meaning of the words it's receiving or the data it's receiving and assigns a vector position to that. Now, there are specialized embedding models for certain things, but for your everyday business data, you're just going to need something simple like OpenAI embeddings. You're going to need to make sure you have an OpenAI account set. So you're just going to go to platform.openai.com/API keys. Make sure you sign up if you haven't before. And then once you're in there, go to the API keys section, create a new secret key, give it a name, create the secret key, copy that. And you're going to go back and make sure that you create a new credential. You're going to put in the API key, leave everything else the same. It's going to do the same again, test. If it goes green, it means it's successful. And then we choose an embeddings model here. So now we've got to choose a model. We're choosing between the text embedding 3 large, 3 small, or ADA 002. Now the easiest comparison I found for this was here. The only difference between them all is the granularity at which they split the documents and the words in those documents, the data, into different vectors. So the embedding small model has fewer dimensions in the vector database. So if you remember, vectors are placed on a 3D plane. So it's got 1,536 dimensions to that vector. So that would be individual numbers. It's significantly lower cost than the other models and still performs well on benchmarks. So think of the embedding small model as suitable for short, simple documents. So this might be your meeting notes, and you want to use this where you want to save a bit more money. The large embeddings model is as it sounds. It's bigger or represents a specific set of data by more vectors, which means we can search to more granularity. We'll get better results, and you can see that by the benchmark performance, but at the expense of more dimensions, which is going to cost us more. So the data here in the dimensions means that each vector we save has more data points around it, so that it's easier to search. We can have a higher accuracy search. And then the embedding ADA 002, I believe, is an older model, which was a budget-friendly general purpose tasks. So whilst we are looking at complex financial documents, you can see inside the Netflix documents themselves, we've got 84 pages of different documents here. So what we might want to consider is actually using the embeddings large model. Now, I'd normally recommend using a cheaper model and testing, but I think for such a complex document, I'm going to start out with the embedding large model, and we can test and see if that performs well, see if that breaks it up into enough granularity that we can search for specifics here. Now, the other aspect we're going to have to connect here is a document loader. So this will now solve the issue of the fact that we were receiving a binary file here, because we can actually tell this data loader that it's going to receive this binary file. But if you're receiving text, then maybe we would use JSON here. And we're going to tell it to load all the input data. And it's automatically going to detect the data format here by the MIME type, which is application/PDF, or we can give it a specific one like PDF. But let's let it auto detect and do the work for us. And then there's other information which we'll cover a bit later that we can add as some context for this data, such as metadata. But for now, we're going to leave it straightforward. So this document loader now, we have to tell it, if we click on the text splitter, how we want to split this document. So if you remember here, there are multiple ways to chunk a document. And I've got a summary down here. We could split it by fixed size chunks. So we take the financial documents and we say every 200 characters, split that and call that a vector. So this would be really useful if we had something like FAQs or procedures where we have like a question answer, e.g., how to reset your password with an answer, steps to troubleshoot login issues with an answer. But it's probably not going to make a lot of sense for our complex financial documents here, because we could lose some context if we split randomly in the middle of a line after 200 characters, say. We've then got context-aware chunking. For example, we could have a product manual in Notion, and there could be key boundaries to look out for, like subheadings. And the context-aware chunking says, okay, at every subheading, split the document. So we could have introduction to product features, step-by-step guide for installation, troubleshooting common errors, all has different headings, and it would split the chunks from the document based on those headings that we define. So we want H2 headings or subheadings to be the split there. And then we've got finally recursive chunking, which is probably going to be the most applicable in our use case here. And it's optimal for layered documents where there's lots of subsets of information. This could be like where we have a legal document that has lots of subpoints under a law, or any information that's very hierarchical. And you can see this strategy is ideal for large complex documents where users may need highly specific information, such as how to configure software settings. So that's probably going to be the best one to try in our use case here. So we've got the character text splitter, we've got the recursive character text splitter, and we've got the token splitter here. So we're going to go for the recursive. And now we've got several options in here. We have the chunk size and the overlap. So the chunk size is just at how many characters are we going to split. So let's just leave this as default right now. The chunk size of 1,000. And the chunk overlap is how much of the context needs to be in the previous chunk as well as the next chunk. So if we leave this as 0 here, every chunk will be an independent isolated chunk. Whereas if we add something like 200 here, it means the last 200 characters of the previous chunk will be the first 200 characters of the next chunk as well. So obviously this takes more tokens, but it means some context can be used between the chunks here. Now we are obviously setting these arbitrary limits and we're going to test it. It's hard to determine upfront what the best chunk size, what the best chunk overlap, etc. is going to be for your use case to give you the best results. But there is some way of making it a bit less technical and a bit less guesswork. And that's good to go to vectorize.io. Let's sign up for a free account here. And it helps you build RAG applications. And if we go into this run a RAG evaluation, it says test chunking and embedding models using your data. So all we need to do here, let's call it test, is upload a sample of our document if you're comfortable doing so. So this is our Netflix document. And we're just going to leave it on the default settings here. And we're going to start the RAG evaluation. It's going to run through our document, test it on certain benchmarks, and come back with some suggestions on which would be the optimal embedding model, the chunk size, and the overlap for us. So we don't have to do the guesswork here. It's going to do a lot for us. And this is why we do these tests. So I've run the test. It's come back with different benchmarks around relevancy i.e. it's tested it on certain things and said, using this embedding model, the chunk size and the overlap, how relevant were the results it returned when it was asked a question. And you can see it's asked it 27 questions based on the data, and said, okay, the recall here is very high, 0.9519. The recall is actually higher on the large embeddings model, but the relevancy of the results was much higher, 0.65, on the small model. So actually, it's suggesting here that we go with the embedding small model, as it has the best balance. So let's go back. It said 50 for the chunk overlap, 500 for the chunk size, but actually we're going to switch out this embeddings model now because it's recommended the small for the best combination of recall and relevancy. We're just going to move this over here. So that might be quite a few new terms there, but you can think of this as just, we're taking a document, we're deciding what methodology to split it into chunks. We're choosing a model, i.e. an embeddings model, that determines the specificity at which we recall certain data from our database, but at the expense of cost. So if we go large, we have a higher cost, but can be more specific. We've used vectorize.io to tell us that actually small is good enough for this data set. And then we've said, okay, we want to split this document, and we've chosen the recursive because recursive means that it will start at the highest level separator. So in this case, it might be paragraphs. And if those paragraphs exceed 500 characters, it will then go down to the next separator. So it might be a chunk size of 300 because the paragraph is 1,000 characters long. So it says, okay, the paragraph was too long, but to retain context, we're going to go down to the next separator, which might be subheading within the paragraph. It might be full stop. It might be new line. And it basically will then split out that paragraph, but keep those paragraphs adjacent to each other in the database when we load them in, so that we've got that context and that flow, as well as choosing 50 characters of overlap. So we've got context between the previous paragraph and the next paragraph. So a lot to take in there, but what we're going to do now is load that document into the database. So we're downloading the financial document. We're going to load it into the database and show you exactly what that looks like. So let's go ahead and we'll just test the workflow. And that's now downloading the file again. And it's now starting to load that into our Supabase database. And we will go into Supabase and we will see what that looks like once that's all loaded in. So it didn't take long at all to load in, and it's loaded in 667 individual items here. And if you go into the output logs here, you can see every single bit of content it's loaded in. So these are the equivalent to what we call the chunks. And it's also loaded in this metadata without us asking to. And you can see it's got metadata about the whole document and also which lines it took from the document. So this will be 34 to 35. That was 29 to 33. So loaded in some really interesting data that we'll be able to search on that. And you could see we could make this a bit more specific, and we could have changed the title of the document to give it a bit more info. But let's go into Supabase here and refresh the page. And what you'll see are the 667 records, like we said. And you can see, if you look at some of the contents, for example, here it's taken the table of contents and it's split that chunk in this content row, it's a chunk, into two because we've gone over the 500 characters limit. So you can see here we've got the context up until item 7. And then the next one we've got item 7a. And that's that next chunk. The next one's got up to item 16. So you can see how different vectors store different pieces of information. It's got the metadata stored and it's saying, okay, we've stored this line to this line from the document. And then it's also got the embedding or the vector representation. So this is really crucial, remember, because we've turned this text here into an embedding. And the reason we've done that is it's really efficient to search similar embeddings if we're looking for certain terms. So say, for example, we would ask, and we can try this, what is the table of contents of the document? That query would be embedded into a vector, and the vector position would be similar to all of these similar chunks that have table of contents. It would be able to efficiently find those in the vector database and say, okay, spit back to the user the most relevant information, and it would pull back, for example, the table of contents rows here, and we can try that. But it's great to visualize it inside the database and have it with this metadata here. So for a very simple use case, that is the ingestion stage that we talked about there. So actually, once you've done that once or twice, it's very straightforward. Let's open up a note here. Let's just call this ingestion. I'm always very keen to label everything clearly and have clear run-throughs so that when I revisit these documents or workflows, I know exactly what's going on, and it's good practice to have. Let's cover the retrieval stage now. So we've loaded the document into the database. Let's take off this test here. Let's copy this note, and let's just start creating our retrieval journey. And remember, we've loaded this document into our database so that when we ask for certain information from an LLM or AI node, that information is going to be returned back, or the most similar information is going to be returned back, so that our LLM or something like ChatGPT can use that similar information to give us the right answer. So we're going to need to create a prompt that says, okay, based on the user's question, retrieve the most similar data points and use that in your response to answer my query. So very straightforward if you set up a chat node before, but here it is as a graphic representation. We've got the user question. It will be embedded as a vector exactly like we saw before. It will then be used to search the vector database and return that for an answer. So what we're going to need to do is attach a chat query, so where we can answer questions, so a chat trigger, sorry. So that's just going to enable us to easily test this inside our workflow environment, because we can open a chat here, say hello, and it will run and it will send that chat message. We then need to connect an AI agent to this that's going to receive the chat input from the chat trigger. And you can see already that we tested. It's passed through the hello as chat input. But we're going to give it a specific system message. Instead of a "you are a helpful assistant," I've crafted a very brief prompt here that you can copy out. You're a Netflix 2024 financial document assistant. So we've been quite specific here with our first example, but you'll see how we can apply this to more broad RAG use cases going forwards. Your job is to answer questions using the files in the vector database. Check the database first, search for similar text chunks using RAG. If you find matches, use them to answer the question from the user. Always say which chunks you've used. So we just want it to tell us the chunks so that we know it's using actual data. And if no answers found, say I couldn't find this in the Netflix 2024 documents, never guess or invent answers. And then we've got an example response here. Netflix grew revenue in streaming services by 25% in 2024 with a reference to the chunks. So we've given it an out and we've told it the steps it needs to take, because this is effectively a tools agent that we need to connect to the vector database. But first, let's just connect it to an OpenAI model. And let's just use GPT-4o Mini for this first example. We want to give it a simple memory just so it remembers what questions we've asked it. We can also set this up with Postgres, but we're not going to cover this right now. So we'll have the simple memory. It can remember the last 15 messages we've sent to it. And that's going to read the memory before it answers any questions to check it's not duplicating answers, etc. And then within the tools, the vector stores are quite high up on the list. We're going to retrieve from our Supabase vector store, and you can see that this opens up. We've connected to the same credential, and we're retrieving documents as a tool for an AI agent. And that's exactly what we're doing. Let's give this tool a name. Let's just call it the vector store. Let's just call it documents. And then we can just use the description that's already here. Work with your data in Supabase vector store. And then from the tables, we're going to just say you're going to retrieve from the documents table because we saw in our Supabase that that's what we're pulling. And then we're going to tell it, don't pull more than the 5 most similar chunks, and pull the metadata as well. If we wanted to select certain metadata and pass in metadata in the message, like say we had a 2024 document and a 2023 document, we might pass in metadata when we initially load the documents here. So we add to the default data loader here, metadata, and we might say the or the year or of that specific document. So that's all we're going to do there. We're now going to connect an embeddings model, and we need to use the same embeddings model because if you remember, the embeddings model is going to convert our query into a vector. If we're using a different model, it's going to be looking for a different set of vectors, so it won't work. So we'll connect our embeddings model, and we use the small model as it's suggested in vectorize.io. And let's just run that to ask a query. Let's say hello to check it's working first. And perfect, it's come back. How can I assist you today? If you have any questions about Netflix's 2024 financial documents, feel free to ask. So let's give it a spin. And let's ask it about the table of contents in the document. We know that that's something that's stored in the database. And what we can see if we go into here first is we can see inside the Supabase vector store the response of the 5 most relevant pieces of information it's pulled. So, and you can see it's pulled multiple vectors where the page content contains table of contents. And it's finally in its 5th chunk pulled these various titles like business, risk factors, unstaffed comments. So let's see what it's actually pulled here. So it's got part 1 and part 2. It's got business, risk factors, cybersecurity, properties, and it's gone all the way up to item 5. I know for a fact by looking back at the document or search table of contents, you can see it's effectively read this section and started pulling these. So it's pulled these correctly, but it has not included all of the, if we go back and we tell it that it's able to retrieve up to 20 most relevant, if it will have a better result here. Because from the outputs of the actual vector store, we can see that it's pulled 5 chunks, but that wasn't enough information. So maybe we need to pull more. Okay, and now it's given us 5 parts here. It's given us part 1, part 2, part 3, and part 4. Sorry, 4 parts. And said this information was sourced from chunk 12. So let's go back to the document here. Let's go into part 3. We've got directors, executive officers, and executive compensation. But we can see from part 3, it's not pulled all of the information. Let's have a look at part 4, item 15 and 16. And again, from part 4, it's not pulled all the relevant information. And then if we go into chunk 12, it seems to have made up that it was pulling from chunk 12. So this highlights one of the limitations of conventional RAG. And I've seen a lot of demos. And part of the reason that I am creating this video is I've seen a lot of demonstrations on YouTube in particular, where they have this small document that's loaded into the RAG, and it's very easy for the RAG to pull the correct information. But when you're dealing with business data, you often have large documents, more than 84 pages that we're dealing with now. And I wanted to highlight the limitations of RAG and show you how you can overcome those using a few different methods. But first, what we're going to do is we can see it's not brilliant at returning full lists like the content section, but let's give it a few more queries, see if it can perform well at pulling specific details from the data, specific details that we'll look through the Netflix to find. So one of them is, let's look for streaming revenues. Let's look for revenues. In fact, what we'll do is we'll go back, and this is a good way to test it, because we might not know the exact name, and that's the point in a vector database search, is actually we can just search a term that's similar to streaming revenues, and hopefully it can pick out the right data. for us, and then we can find that in the document itself. So we'll do tell me the streaming revenue for 2024, and that will go and search the database. And it's come back straight away. The streaming revenue was 39,000,096, which represents a 16% increase compared to 2023. And it's even given us a reason. It was driven by an increase in average paying memberships and price increases, which makes a lot of sense if you use Netflix. So let's search that number. And there's 6 results that we can see that have that number. And you can see streaming revenues was 39, increases 16%. So that's exactly right. It's pulled the specific information. And again, there's just several sources that back that up. So that's great. It's performed really well there, pulling specific information from that 84-page document. And you can see that's like 67 pages in, and the first instance is 22 pages in. So perform really quickly. And that's because everything's stored as a vector. I have a feeling these chunks are not correct though, 5, 12, and 15. Chunk 5 is here, nothing to do with it. Again, nothing to do with it there. And again, nothing to do with it there. So it's kind of just making up the chunks, which is fine. We don't need to know the chunks, but let's see in the return if we've got anything to identify the chunks here. And it doesn't seem like we do. So we've got some metadata information around the different lines. So maybe for now, for ease, because we don't need it, let's just remove that from the prompt. I'm going to ask it a more generic question. Give me the streaming revenues breakdown per year, and let's see what information it can pull now. And it's managed to pull the different years that it has on here. And because it's got memory, this simple memory up here, if I just ask something generic, like give me a further breakdown, it will understand that I'm talking about those streaming revenues, because if we go back to the first here, we have the streaming revenues here, but it also has DVD revenues and all of this information. So maybe if I ask, give me a further breakdown of operating costs and DVD revenues for those years. And I'm amazed to see that they still made some money in 2023 from DVDs, but none in 2024. So it's finally out. So it's given us all the different operating costs here. So let's just check one, operating cost of revenues. And I think it's possibly multiplied this all by 1,000 by accident, but let's see if we've got this number. Costs of revenues. So it has understood the query there and pulled the correct number again. It's then got cost of sales and marketing. So that was on page 24. Again, we've got from page 25 some different costs. So it's understood that these are all the different costs, and it's gone down these different tables and extracted the values. Now we're lucky that this PDF has all text values, and the way I know that is because I can highlight this row. If we're searching for something that's embedded in a table that's an image or a graph, then we're not going to be able to find it because it's not going to be able to extract the data correctly. So for something like this, a stock performance graph, we have some of the results in here, the comparison, but actually we won't be able to extract any information from the chart itself because this is an image, not text. So let's see if we search the 5-year cumulative total return versus the stock market, because that's what that was showing. And it might have some text underneath, but if not, it might not be able to answer the question. There we go. However, specific numerical values detailing the cumulative returns are not provided in the documents retrieved. If you have access to the performance graph or detailed figures from additional sources, that may provide the exact returns needed. So it knows that we have some sort of information in here, and it's given us what it can, but it cannot extract anything from that chart. If you were looking to extract information from the chart, we're not going to build that in here, but it's something we've touched on inside the school community, which you can check out in the description and the comments. But you'd have to use some sort of OCR, optical character recognition software. So that would take images and extract information from those images. A popular free to use one is Mistral OCR. And you can see it's got examples here of like a math textbook and what it returns in the OCR results. So you can even pull out things like formulas, but what it does is it converts all of this into text that you can use, so you can see how powerful a model like this would be if we were to extract the chart directly. And we cover more about OCR in the community itself. Let's ask it another question. What was the earnings per share? And we can see it's got a basic earnings per share of 20.28. Let's go back into the document. It's always worth checking something like this. And we've got the basic earnings per share from page 40, 20.28. So you can see from that small example of an 84-page document and it's a financial document with a ton of information, that although not perfect, the embedding model and the retrieval that we've chosen is actually pulling out really specific information when we're really specific. It struggled a little bit with the context of what the full table of contents was, which is a potential limitation, and there's a few ways to look at that. So I'm just going to ask it again, what is the full table of contents for the report, so that we can come back and revisit this limitation that we found before, again returning part 1 and part 2, and we'll see exactly why that limitation exists. If we actually go into the Supabase database itself, you can see that table of contents is clearly present in chunk 14. But when we move on from chunk 14, we've got no reference that this is actually part of a table of contents. Again, chunk 16, no reference, etc. So we're lucky that it returned these parts. And in fact, I don't think it even returned 7. Let's have a look back here. Yeah, only went up to part 5, despite the fact that even in our chunk, it had up to part 7. Now, it should have returned the rest of that chunk for sure. That's just a bit of a mistake there. But how can we give something like Supabase more context so that it understands this is actually part of the table of contents? It's missing this context here. So when it's doing a vector search, it's finding the words table of contents or things similar to that effect, but it's not intelligent enough to allude that any items are table of contents pieces. And it's kind of right in doing so, because if you think about how this document's laid out, we'll have multiple other parts of the document which will be split up by items or bullets, and it can't assume they're all table of contents. But there is a way to help contextualize this, and we're going to visit Anthropic's Contextual Retrieval Guide, which they brought out in September last year, and it aims to get around these limitations of lack of context within chunks, and it claims to actually reduce the number of failed retrievals by 49%. And first, it alludes to actually a much simpler solution that we've spoken about before, is actually sometimes you can just put the entire set of data up to about 500 pages in the material itself, of material in the prompt itself, because if you're using something like Anthropic or OpenAI, all of that data will actually be cached inside the prompt. So if you're asking questions multiple times, the tokens will only be used once, because it will be sent into the prompt, because it will be sent into the LLM, cached in the back end, so that it's all stored there and can be easily searchable. However, it notes here that as the knowledge base grows, you'll need a more scalable solution, which is where they've come up with the idea of contextual retrieval. And contextual retrieval means that actually we're going to spend less because we're not having to cache 200,000 tokens, for example. And I think the best way to illustrate this is to go to Anthropic's example here, and you'll see exactly how we could use this contextualized chunk in our table of contents example as well. So we've got an example of some SEC filings here, and we've got an original chunk, which is the company's revenue grew by 3% over the previous quarter. And you can see that without any context yourself, you have no idea in what year, what quarter, and any of the context surrounding this 3% revenue growth. So the contextualized chunk aims to change that by comparing the actual chunk that we save, which is just this sentence, to the full document. So it looks at all the context that came before it and all the context that came immediately after it, and says, okay, what does this sentence actually mean in context? And with the contextualized chunk, you get it's from an SEC filing on Acme Corp. So it's included the company name because this SEC filing's report could contain hundreds of companies. And it's about their performance in Q2 2023. The previous quarter's revenue was 314 million. The company's revenue grew by 3% over the previous quarter. So you can see that actually having that initial context put on the start of the chunk, now if we were to ask about Acme's company performance, it would never pick up this original chunk, but it would probably pick up this contextualized chunk. So adding context into the data before we upload it into our vector database is a solution to get around the limitation that we saw of incorrectly retrieving something. And it's given an example here of how we'd actually prompt an LLM after we've chunked the document, but before we embed the vectors, we'd pass in the whole document as context and say, here's the chunk that we want to situate within the whole document. Pass in the chunk, like this SEC filing sentence here, and tell it, please give a short, succinct context to situate this chunk within the whole document for the purposes of improving search retrieval of the chunk. Answer only with a succinct context and nothing else. So you can see how that would take us from the process that we previously had of breaking chunks down and embedding them straight away into breaking chunks down, adding context to every single chunk, and then embedding them afterwards so that the context is stored in the data directly and is relevant and searchable. So we'd go from something like this here, and we can see this in a moment, where we've got just random items from the table of contents, and it would say something like, this is part 2 of the table of contents for this type of document, etc. So we pass in the context, and then when we ask for the table of contents, it's more likely to pick it up because actually the context is there. So the semantic meaning is much more likely to be picked up. So if we jump back to the diagram that we had that showed RAG, I'll show you how the only addition here for our contextual RAG is that we're actually just inserting context before the embeddings here, but we're actually creating the context using an LLM stage. So what we're doing is chunking. We're then putting in, let's just call it a context LLM. So we say for each chunk you receive, give me the succinct context based on the before and after in the document, and then add that context into the chunk, follow the rest of the process exactly the same. So embed it in the vector database or create a vector for that chunk after the context has been added. That's the only difference. We'll go back to our workflow here, and I'm going to show you exactly how we can implement this here, and then we can test it on our contents table to see if that has made a difference. And when I was out looking for ways to recursively chunk the data without using the embeddings models here, without using the data loader here, I managed to stumble upon a video by Mahmout, who's got a great channel. Definitely check it out. And he has this workflow that basically shows you how to implement this contextual RAG. Part of that that's important for this workflow, I've downloaded, and we're going to plug it into our workflow here and change a few things up to match our settings. But thanks, Mahmout, for coming up with this really smart way to recursively split, create context for chunks using that Anthropic prompt plus a bit more, and then summarize it so we can pass it in through the ingestion phase with the context. So we've got this snippet that we're going to start adding in, and we'll go through each node individually to show you what's happening. But we'll go back to the ingestion phase here. And actually what I'm going to do so that you have all of the workflows available is I'm going to keep this initial workflow up here, and I'm just going to duplicate it, and we're going to create a new table because we can always then refer back. And the retrieval we can keep the same because we can just change the table, but we can always refer back then to the multiple workflows. So this is the standard RAG that we saw the limitations of, but still pretty good. And this is going to be the contextualized RAG. So our data structure doesn't actually need to change because if you remember, the way we're going to insert it into the data is actually the content in the text field of Supabase in this content field is going to be exactly the same, but it's going to put the context at the start of the chunk, so it's able to be easily searchable. So it's going to have something like this: succinct context, and then original chunk, or corrected version if necessary. Mahmoud has already added some additional really useful information in here that he mentions in his video. He takes the standard approach by Anthropic, but you notice there were a few mistakes where a chunk would often split on a percentage or on a number and lead to you having incorrect data, which would then force the LLM to hallucinate with incorrect data. So by including this additional set of instructions, we're able to mitigate that, and it's able to look at the previous context and reconstruct any mistakes. So it says return the original chunk exactly as provided unless a correction is necessary. If the chunk contains an incomplete number, percentage, or entity, correct it using the full document. If part of a sentence is cut off, reconstruct the missing words. If the chunk is part of a table, include the complete table entry to maintain data integrity. So it's like, on top of adding context, don't chunk in the middle of really important context that needs to sit next to each other. Like, don't chunk half of a table. So for example, it might decide here that actually a relevant chunk is the whole table of contents, and then just add the context to that rather than chunking at every 1,000 characters in there. The other thing that's really useful in this workflow is the recursive splitter. So like I said, there's no inbuilt way yet in N8N to split your chunks. So this code node will help us we'll put in our chunk size and our chunk overlap, which I believe was 550. And what it will do is it will say, okay, let's try and split the remaining text into chunks. And it does that first, like we mentioned, recursive splitting is like looking for the different hierarchical levels. So first we'll try splitting at paragraph level. If that's not possible, split at sentence level. If you can't do that, split at word level, so it goes down the hierarchy. And then if not, it forces it to cut at a certain chunk size. So it goes through all the different hierarchies there to try and maintain as much context as possible. We're then going to just call it the chunks, and then those are going to be passed into our prompt, which you can see loads in the full document data as well as the chunk. And it's about adding the context to the chunk. So that's really straightforward. We'll just rename this to add context. And then the summarize afterwards just puts it into a format that we're able to then pass in to what the Supabase vector database expects. It's expecting a text input field, and that's why we call it text. We also pass in a separator because what we can do now on our second version of this is we will split the code. Instead of using a recursive character text splitter, which we're already doing in the previous stage to initially split the document, we're going to delete this. We're going to start with a character text splitter. And now we're going to say, okay, let's do 550 again. And then the separator is going to be this custom separator. And the reason for that is because we're saying between all of the fields and all of the data that we receive, we're going to add this custom separator, which is split. And this could be anything. This could be a exclamation mark, etc. But this is something that's not going to be naturally in the text. So it's good to pick out something like this, which is totally unique. And what we're going to be able to then do is feed in the split chunks already into our vector database, which is going to identify to split every time it hits this separator in the text with a maximum chunk size of 500. So if that all makes sense, let's move on to actually implementing it within our workflow and test out if it works on the table of contents. It's a really intelligent way to add context to our RAG. So we're going to implement it now. So one of the additional stages in the ingestion here that will improve our RAG ingestion is that actually we should allow it to have multiple inputs. So it might not necessarily be a PDF we're loading into our RAG. So by having this additional stage where we basically just stringify the previous data that's received, We're enabling our RAG to take in multiple document formats. So an additional node we're going to need here is extract from file. So in this example, we know we're receiving a PDF from here. So we'll have an extract from PDF node that we will connect to our Google Drive. And before, we said in our data loader that it would be a binary data type. Now it would be a JSON data type, and we're saying to load all input data. And that just means that we're now more flexible to multiple input types. So instead of having a PDF and always thinking it's going to be a PDF, we can load in lots of different types of formats. You just need to add those down here and then connect them to this document data. So say we also had, if I just copy that, say we could also load in CSVs, for example. Perhaps the file is going to be a CSV. So what we'd have to do here is say, instead of connecting both of these, we'd put a switch node in. So the switch node allows us to say, if the file type is this, then perform this route. If the file type is this, then perform this route. So if it's a PDF, go down this route. If it's not, go down this route, for example. So we'll connect the switch node and we'll give it another route. Disconnect this. Let's execute the workflow so that it can start and show us what the file type is. And if we go into the expression here and put $binary.data, so we're digging into the binary data here, and we just say file type, let's see what that comes up as. So that's showing PDF. So if that is equal to PDF, then we're going to go the PDF route. We'll copy that for our second route, which we've said is for CSVs. If the file type is equal to CSV, then go the CSV route. And now you'll see on the output that we've got two routes that it can take. Let's connect PDF up there. Let's connect CSV down there. So now, based on our input type, it will decide a different route, but this document data node, or this edit fields or set node, will just take the stringified version of the data, no matter which version comes through. The other thing we did before, which we said we would change, is we connected before to a specific file. Let's go and find the actual file drive instead. So say we wanted to monitor any file uploaded to the drive and make it dynamic. Every time we upload a file to the drive, it will upload the document into our vector store. Then instead of downloading that file directly, we will change the trigger from a manual trigger to be a Google Drive trigger. We'll go down to triggers and it will say on changes involving a specific folder, every minute, let's monitor, and we can say the URL of the folder here. And let's say when the file is created. So instead of this manual trigger, we've now got this new trigger. So let's delete the manual trigger. Let's try and run the new trigger. And let me try and find the folder from the list instead, as that doesn't seem to be working. It's connected to the wrong Google Drive, that's why. So let's go by URL again. Let's fetch a test event, and it should come back with that file. There we go. We've got one file there. And we can specify in here if we want it to do just certain files, but we don't. Let's leave it as all. And then we still need to download the file. But now instead of taking it by the URL, let's take the ID of the file from the previous node. And we'll pop the ID in there. And let's just check that that actually downloads before we go any further. Great. So that has downloaded. It's exactly what we thought it was. And now it'll be processed. And if we let it process, it knows that it's a PDF from the file type. And now we have issues here because actually the field we're receiving is called text, not data. So let's run that again. And I'm just going to pin this here so it speeds it up. We'll download the file. We can't pin that. So now it's successfully pulled all of the data. If we go into the JSON here, all of the data from our doc. The same would happen if it was a CSV. We can add more routes here. That was just a demonstration. So we've made the input to ingestion dynamic based on a folder. We've extracted the content from the folder and allowed for multiple file types. If we just revisit our document here, The next stage is splitting it into chunks and adding the context to those chunks. So that's where this new part of the workflow is going to come in before we eventually add it back into our vector database. And we're going to create a new table to add that into. So I've got to remember to do that. And actually, instead of creating a new table, I'm just going to go back into this table and we're going to delete all of the rows. If we change this to 1,000 rows. Great, so we've got a clean table, so we can actually add that context into our table there. So what we're doing now is we are manually, with the code node, like I mentioned, splitting up our document into chunks recursively, i.e. based on the structure of the input document, which is the most appropriate method for most. We'll come back and we'll add notes to this workflow so that we can see exactly what's going on from a high level, but for now we'll just test it out. So before we add any context, let's see what chunks it breaks up into. And it's a good idea to always test this stuff out. And let's just pin some data to speed up the tests here. So you can see that with a chunk size of 500, it's cutting off some important context between these chunks, and each of these numbers represents a different chunk. So hopefully the context that we're adding here will help. And you can see that it's split it into 730 chunks here, which is a bit more than we had before. So what we're now doing is we're adding context. And the reason we've chosen this Gemini model is because of the cost of it. It's actually free to use for a certain rate limit. And then even after that, it's incredibly cheap for input tokens. You get per million tokens in USD, the input is 10 cents. So incredibly cheap. One of the cheapest models that exists. And it's actually very good as well, especially for a simple task like this, where it's just categorizing information and adding a summary. So let's just pin that data as well to speed it up. And let's test the workflow. Let's fire it through Google Gemini and see what has been added. Let's check inside here that we're receiving the data correctly. So we've got the document data.item.json.data, which is correct. That's being received correctly. And then we've got the chunks being received like this as chunk. And you can see that on the free plan, it's 15 requests per minute versus the paid of 2,000 requests per minute. So we are paying a little bit here with the speed that we're able to do it at. So let me talk about a limitation here. So I've been waiting for around 10 minutes. We passed in 730 chunks, and you can see it's only done 87 items. So this is a good method if you can wait for your data, if you're not precious about time. But you can see this extra processing stage where we add context does actually add a lot of time to the ingestion phase, which makes it quite complicated when you want to update the data rather than just load in data at once. So we'll talk a little bit about the options we have here for one, updating the data in our database directly, and two, what are the alternatives to RAG? So we're going to touch on CAG and how to set that up in N8N, because actually with something with less than 200,000 tokens, like it mentioned in the Anthropic guide, it might be better off and cheaper, particularly for large financial documents like this, to actually just use CAG, because they're not going to update very frequently. So all we need to do is load in the full context using CAG. So we'll talk about those limitations after we've touched on the results of this. An alternative here is we could just change the chunk size for demonstration, and that's what I might do in a second. Change the chunk size and reload this. We'll limit the amount going in just so we can demonstrate that it actually pulls the correct context and adds context to it. So let's update the chunk size to 1,000, and let's actually have 0 overlap, because if we've got context, then we don't really need the overlap necessarily. So we're going to unpin this data. We're going to rerun it. And we're also, just for the demonstration, going to add in a limit node, which will restrict the number of items that we pass through. Let's pass through, say, the first 50 chunks so that we're not waiting too long for a result. And let's pass that in there. So let's see how we get on with that. So this is now run with 50 items with 50 items being loaded in an added context. So we can see on the left-hand side the chunk that was passed in versus what the chunk now looks like. So we've got just this random stuff that was at the start of the document, and the context says beginning of form 10K, specifying document type, period, company information, and file number. So we can see immediately that this is adding some useful context that if we were to query it, it would be much easier to find. So it's added that context. We then, if we search for something like table of contents, we'll be able to see, so there's 8 matches for table of contents here. And you can see that immediately the first one that we already picked up has table of contents for Netflix is 2024 form 10K. But also when we move on to the items that weren't in it before, so we've obviously increased the chunk size, so we're going to get more items in here anyway, but part 3 is still split by the chunk size. So we can see that item 12 is repeated twice because of the overlap here, but the rest of the table of contents has been included here. So we've actually got all of the different items from the table of contents. So hopefully now with that context, we'll be able to better retrieve from our vector store. So let's just pin that data so we don't have to rerun it. And you can see in the summarize that this stage, we've just concatenated the text here in one large field so that when we pass it into our vector database to store here, all we're doing is actually splitting it by the split separator like we mentioned before, with a maximum chunk size of 1,000. So it should work through these, find where to split like here, and split it into individual chunks which will go in our database. So let's pin that data, and we will run that, and we will see what that looks like now in our Supabase vector store. And then we can try with the example that failed before and see if the context has improved our retrieval here for larger bits of context where we struggled before. Okay, so it's saying it's added our 50 items to the database. We'll come back in and we can now see that the 50 items are in the database, and the table of contents here, and we have another table of contents here. So you can see that now it contains the words table of contents. It's going to be much easier to find this through a semantic search. So let's go up, let's remove or deactivate our trigger here. And all we need to do, because we use the same table, is actually just refresh the chat here. So it's got no history. We'll make sure it's working. Great, it is working. It's connected to the table. And let's ask, what's the table of contents for this document? And let's just reconnect it back up. There seems to be an issue here. And for some reason, it just wasn't searching it wasn't searching the vector database at all. So I've just made it more explicit in the prompt here that we got to check the connected vector database documents. And the reason I've done that is in the Supabase vector store here, we've called it a documents tool. So I just want to make sure it knows that. So we've actually asked it, what documents do you have access to? It's inferred that that's actually the table of contents. So it's pulled out all of the different items now from the table of contents. And let's see if it got them all. So let's go back to our actual document. Let's go to the table of contents up the top. And we've got 16 items here. Let's see, item 12, security ownership. Item 12, security ownership. So now you can see that actually adding that context in has made it much easier to pull large sources of documents, where with a conventional RAG database, it would split that and not understand how to access that correctly. So I've come back in here while the camera's been off, and I've just cleaned this up a little bit, just so you know. So we've got the ingestion basic example that we showed first, and then we've got the added context here. So we've labeled up each different stage. We add the context to the chunks. That's the overall. We add the context to chunks, which we know is this second ingestion type. So we've got the file type switch here. We've got where we split recursively into those chunks. we add the context to each chunk and then add to a vector database. So it's just a bit cleaner and easier if we come back to this flow to see exactly what's happening here. So now we've run through a basic example of RAG, and we've seen that actually it can be pretty good if you choose the right embedding model, the right text splitter, which we've also covered as well. We've then seen that it's not great sometimes at returning long lists because it lacks context. So we've talked through how to add context to that, albeit that added a lot of time to our RAG ingestion process because we were having to process every single bit of information. So it would have been 733 items for just an 84-page document. So the ingestion phase, although had better retrieval, was a lot slower, but we were able to achieve better results. But there are still two ways to get around the limitations that we still see in this process. The first limitation is around that we update this static data once in our database, and sometimes we'll have data sources that we need to continuously update. So say we have company documents, company procedures, meeting notes that are edited after the meeting. We want to be able to update those as they come in rather than load them in statically once. So we're going to cover how to do that in Supabase in a second. And then the second area, which we'll move on to CAG for, is actually, this is a very slow way to do it. Can we do this cheaply and easily using cache augmented generation instead, which we'll explain after and show you exactly how to do that inside N8N. So updating data, we're going to move on to a different set of documents. So something like financial documents that are annual reports, you're only going to load in once. So it's not very good for this use case. But something like meeting minutes actually is a really good use case of something that would be possibly updated and we need to update. And we'd also load in multiple documents so we can tackle that use case as well. So in the Scrapes.ai school community, we run 3 weekly tech help sessions a week. And we've got 2 examples here of, if I just remove that, 2 examples here of key takeaways, but also full transcripts from those meetings. So we've loaded those into our Google Drive folder that we're monitoring, and we're just going to remove the Netflix one for now so that we just have these 2 documents. You know they're not PDFs, they're docx, so we'll also tackle how to handle those as an extension on this. But ultimately, the goal of this is to be able to update data directly in our Supabase vector database and show you how to do that. And there's a bit of a workaround in N8N because you can't actually update it very easily directly, and you've got to delete the old rows. So let's copy this workflow down here, and we will make amendments directly to this. For argument's sake, we don't actually need in this example to split into, like, add context to the chunks. So let's get rid of all of these stages and let's simplify the flow. We'll still have the earlier stages, which are the file type switch, because we've got to add a new one. So let's add a new one in here because we know that we're going to be processing docx. And we're also going to need to handle the case where multiple uploads could happen in a single minute. So we're going to need to add a loop here. And we'll just rename this to updating files, as this is our 3rd use case. And by the way, you can access all of these in the school community directly. If you just want a shortcut, see these directly, you'll be able to download the workflow in the school. But as with this video, you can just follow along and build it for yourself as well. So we've still got the Google Drive trigger, and let's unpin any data we have here. And when you're testing these, just make sure that we deactivate any other triggers here so that we're not accidentally loading in a file from up there. So let's fetch the test event from the same folder, and we've pulled through, and we can see actually this is the MIME type. So we can already set up this switch node here, and let's just test the workflow so that it extracts that and we can see the actual type that's coming through. Interesting. Okay, so if it comes through as a docx, it doesn't actually have the file type endpoint, but it does have the MIME type. So what we're going to need to do is just go back and update where we previously assumed this would be okay. Let's call it docx. This is the docx MIME type, which is just like the file type, right? And we'll go back and update these ones, but we just want to update this so that instead of file type here, it's MIME type. And that's more consistent anyway. So we've gone in and we've updated that. So for CSV, it's application/VND, and you can Google these, by the way, .Google Apps spreadsheet, and then the docx we'd already put in, and application/PDF here. I've also gone and updated it here in our previous node, and we'll connect this third route, the docx route, to here. And we're just going to pick extract from text file there, and we'll call it from docx. And again, it just follows into the data here, exactly the same as we had before. Now, when we're storing and ingesting this information now, because we're uploading multiple documents, what we're going to need to, and we need to update the documents, what we're going to need to do is add some metadata to our documents that are being uploaded. So let's just test that workflow, make sure it runs through correctly and extracts the documents. And again, there's a little bit of a error here. So because last time we used file type and now we're using MIME type, we'll change it to .data, but you can see here it's not extracting correctly. Okay, so a step I've just added, if we go back into the download file, inside here we've got Google file conversion. So it's actually hard to extract data from a Google Doc directly. So we've got this inbuilt property here called Google file conversion. We'll add a conversion and we'll say for Google Docs, let's convert them to text. As an example, we could actually convert them to PDF and send them down that route. But it means in this switch node, we should now say instead of this long, complicated document format, the MIME type is text/plain, and we have changed the output to text there. So now it extracts that raw text correctly. And I'm just going to go back up here now that we've changed this to MIME type and change this to .data instead of .text, and that will now work when that's next run. So we've now extracted the meeting data. As you can see, this is one of the weekly tech call meetings. But as I mentioned, we're going to need to update the metadata here so that when we're loading in a document inside our vector database, we can retrieve information relating to a specific document or be able to delete it and update those. So inside our default data loader, inside options, we're going to click metadata here. We're going to add a property and we'll call it ID and we'll call it file ID. And then from the value here from previous nodes, we will just grab the ID. If we close up the switch, it'll be from the download file. There'll be an ID in here for this file. That's on the permissions. Here is the Google ID. So it will pull the ID from the file we've downloaded, and that will upload that with the rest of the data that's uploaded. We're going to load in specific data here, and we're just going to call this JSON.data. So now we're loading in this data field with this metadata. And we can also add any other metadata that we want. For example, the created time. And you can see how this might come in handy if you can query the data by this metadata and say any files that are updated after or created after this time, do an action with that. So in this case, let's go back to our N8N database. We're going to delete the data that's currently there in our demo. And now we've got a blank table. And what we're going to do is now load in that data. And we're not going to use a text splitter this time. So we're going to delete that. We're going to use a recursive text splitter like it suggests. And let's just keep this at 1000. And one additional bit of metadata that actually would be really important for us is the title of the file. So let's call that file name. And we'll pull in the name dynamically there. That's going to be really useful when we're recalling information from specific documents. We're going to keep the small embeddings model because these are very small documents as well. So we don't need to over process it here. And then we're going to do one final thing, which is add a loop node. And that means we can process multiple documents at a time. This one looks a bit crazy, but let's just bring it down here. Let's delete all the attachments, connect the loop here. So this means it will process, if we click in one at a time, go through this process, add it to the vector database, and then we'll connect that back to our loop. So a second item, if it comes in the same minute, will be processed separately. And then we don't need to do anything with the done here, because actually we're not doing any post-processing here. So we're watching that file there. And let's just test one upload to start with. So we'll execute that and it will go through the first document. And we can see from the output that 53 items were uploaded there. So it's split this document into 53 items, cover up the details there. But you see in the metadata, we now have this additional information. So we have the file ID, we have the type, we have the file name, and we have the created time. So if we go back to our build here, and let's go back to our Google Drive, and it's added in the April the 3rd one. So I'm just going to download this document, remove it from this file here, and then re-add it so that it will appear as the latest created file. So that then when we run our second test, hopefully it should pull through that latest file now instead. And there's been a failure here because the document type is different. So we're just going to open that up and then it will automatically become a Google Doc. We'll close that again and we've saved it as a Google Doc instead. So we're going to move that old one to the bin. We're going to run it again and it's now processing. So it's being added to our vector database again. And we'll be able to see our two documents. This one's been split into 58 rows. We'll be able to see our two different documents. If I change this to 500 rows, if I go to the bottom, you'll be able to see in the metadata that this is our other file name. So now we've got multiple files in our vector database. Let's look into how we search that. And then we can talk about how we update it if a file is updated. And we're also going to need to update our AI agent prompt. It's no longer a Netflix financial document assistant. It's just a document assistant using the files in the vector database. Check connected vector database first. Okay, great. So let's try and ask it what files it has access to. And you can see that it's automatically searched the metadata for us. And it knows from the metadata that it's got access to these two files. I'm just going to ask it for a summary of the April 3rd meeting and who attended. Don't include surnames. And then if we lift it up, we've got a summary here. And then it's given us a summary of attendees, which I was at the meeting, so I know exactly right. And it's given a clear summary there. So it's pulling information correctly, and that was from the correct meeting as well. So it's working well. Now what happens if we go back into the chat here and we actually remove me from the meeting? So we remove all evidence that I was from the meeting. Now, if we just do this directly in the document, and this is what you might do with your documents, you might update them, then it's not just going to update if we rerun through this process. What it's going to do is it's going to add the same named document as a new document, potentially, if we've got this file created trigger, or if we add a file updated trigger to activate this as well, then as soon as this is updated, what it will do is it will just load through this again. And all this is doing is ingesting files into our Supabase database. So if we did this, it would add the files as more chunks to the bottom of these 111 records, which actually would then be more confusing because when we ask that information, what files do you have access to? It would say twice that it has access to the same document, but they actually contain different contents. So the inbuilt functionality to do this in N8N struggles quite a lot. So we have to use a workaround. And the workaround for that is identifying the file ID, which we know we put in the metadata, and removing all rows from the vector database for that file ID or file name or however you want to do it, but we'll do it with file ID. So to delete the rows, we're going to add a Supabase node, and it's going to be a delete a row, and we are going to connect that after the loop here, but before we download the file. So what we're doing is we're going to grab the ID from here, and we're going to match it to our metadata in the Supabase database. So we've got our demo account that we set up earlier. We're matching in the documents, and we're going to hit string here. And all we're going to do is say for our metadata, and this is just SQL terminology here that you don't need to worry about. It's just going to be the same every single time. If our file ID, which we called it in our metadata, is a match to the file ID that's passed in dynamically, which actually in our case is ID, then we're going to delete the existing rows that exist with that file ID. So all we're doing is saying, okay, if that file ID already exists, i.e. it's been updated, but the file already exists, let's remove all of that from our database before we import the new one. So let's just double check this actually works. And what we should see here is it recognizes that the file already exists, and it deletes some rows from our database. So to remind you, we have 111 records here. Let's test the workflow. And it said, okay, it recognizes 58 items that have this metadata of file ID. These are the embeddings, the vector embeddings. Let's remove them. We'll go to the database. We'll refresh here. And this should now be 58 smaller. There we go, 53. So it successfully deleted our rows, and we'll just rename that. Which means if we update a document now, if the document already exists, it will delete all rows, but then it will continue as normal, going through the process, loop through the process, and add the new document. So if we were to remove, if we test it again, let's re-upload the workflow, and then let's actually test it in progress. And one setting we need to confirm here is actually if there's no matches to it, let's always output data so that it continues through the loop. So let's test the workflow again. Okay, and now it can't find the file. And the reason is we've not set the file ID here. It's trying to find the file ID from a previous node. So the way we can do this so that it finds the file ID from both the Google Drive file created trigger and the file updated trigger is using a set node here, or an edit fields node. So we're going to add that in, and we're going to connect it in the loop. And we're just going to say at this point to set file ID. And we'll pull it from the previous node, which can be either of the input types. That's why we've left it like that. That will still work because it's getting file ID from edit fields. We'll call this set file ID. And then the download file should now refer to this set file ID instead of json.id. And let's rerun that and see if that now works. So that will upload the document now into our vector database again. And then what we'll do is we'll go and remove some data. So that's now uploading, 58 items uploaded. Let's go back to the file itself. And right now, let's extract the meeting purpose. So if we ask in the chat, what was the meeting purpose? It will go and extract that. From there, the purpose was to hold a weekly tech session for scrapes. I'm going to go in here and update this to the purpose was to challenge everyone to a duel. So naturally, if we ask it again, it will not understand. It will also save this in the memory. So let's refresh that here. And what we're going to do is we are going to load in the document. And if the file has been updated, it's recognized that there is a file that exists with that. It's deleted those rows, and then it's come back and added it back to the database. So the best way to test this out is to actually just open our chat again and ask what the meeting purpose was. And we can see if that pulls back the new meeting purpose, which was the updated data. And it doesn't, so something's gone wrong there. If we check on We're just going to run this again because it seems to have not updated the metadata correctly. Okay, I understand the issue now. Inside the delete rows, we did not update this to file ID. So now it will correctly understand if the file existed already. And it's saying the file did not exist already. So what I'm just going to do is we've had a few errors here. So I'm just going to delete all of these rows out. And we're going to start again. So let's just refresh the conversation. I've loaded the data back in. And it's still having trouble picking up the metadata. So there must be something wrong with the way we're grabbing metadata from the previous stage. So if we just test and upload, we can go and figure out exactly what's happening here. We can see that all of the metadata is being not found, probably because this is called file ID, but actually instead of taking it from there now, we can take it from our set file ID node. Where is it? Set file ID .item.json .file ID. Here we are. And we'll do the same for here, but change that to created time and this to set file ID.item.json.name. But what that means is we need to go and add created time and name to our actual set file ID and pull those fields through as well. Created time, name, and then like we did before, pull those through as an expression. So we've got created time there, and then we've got name, and that will just pull through from the previous step. So now we've updated all of those. It will understand which one is the 27th. We'll delete all the data again from our Supabase database, make sure everything is gone, and start again. Let's reset this. Let's test the workflow. It should now upload with the metadata. And it was never recognizing there was a file with the same ID because it couldn't actually search for ID because it didn't exist. So this should now have the correct metadata uploaded, file ID, file name. Great. Let's now ask it the same question, and that should come back with the new information, I hope. So let's go back to Supabase, and you can see that the meeting purpose is now to challenge everyone to a duel. If we go back, let's update this to the meeting purpose has changed. We will reload the document in, and it should now recognize that the file already exists, delete those rows, and update the new information in that file, i.e. upload the document again as chunks. And we can see that it's now processed the delete stage, and it's now gone through and added that new file. So let's update this. Let's check the meeting purpose. The meeting purpose has changed. Great. So it has deleted it. It's taken the new rows from the file and then updated that accordingly. So we've now got a full RAG. We've learned about how to build out a basic RAG, the limitations of that. We've looked at how to add context to make the RAG perform better. And now we've also talked about how to update files directly in the RAG by deleting them, which solves the limitation of having static data, which you often don't have in your business. We will now move on to the final step of this, which solves the limitation of this taking a long time to do, which is cache augmented generation, or CAG, which is a newer, more popular technique, and I'll show you exactly how to do that in N8N with OpenAI and Claude. If we jump back to our diagram here, RAG is feeding in our data little by little. We've seen that now with the context. CAG, or cache augmented generation, is as it sounds. We add a large document into the cache of the LLM, i.e. it's processed once and stored as a very efficient set of data that's easily discoverable. We store that in a cache, and each time the user asks a question, it just refers to that cache, adds all the context. So it's like putting all of the context back into our prompt, but it's automatically cached for us to use fewer tokens and cost us less. The benefits of CAG is it actually is really easy to set up in N8N. Very quick retrieval because we've not got to go through an additional source like a vector database. And it's often more accurate because it has all the context. The issues with it is when we've got documents that are harder to update, but also if we've got documents that are over 500 pages, say, maybe even less, and we're adding documents again and again and again. So say it's like a meeting repository, eventually we're going to overflow that meeting repository with too much context, and we'd be better off storing that in a RAG database where we can extract based on similarity searches versus trying to store all of that data and adding to that every single day inside a CAG flow. But the ingestion and retrieval stages all come together in CAG, so it makes it a lot easier to do. Let me just remind you why CAG came about. So when LLMs were first becoming popular, we had the models like GPT 3.5 Turbo, and you can see that the input token limit and output token limit were approximately 4,000 tokens, which equates to around 3,000 words. So that's not much context at all. That's about 6 pages. So RAG came about RAG became popular because actually the token windows were relatively small, and then the models that had a larger amount of token windows were more expensive. So GPT-4o, for example, had a much larger token window of 128,000 tokens, but actually it was $2.5 per token. So RAG was a way to feed in data little by little so that we'd save that token cost, but also respect the token limits of the smaller models. Fast forward to 2024 or late 2024 when Gemini Flash 2.0 came out, the token limits are now not the same as what they were. We've now got Claude 3.5 Sonnet with 200,000 tokens, and also Gemini Flash 2.0 accepting up to 1 million tokens, which is absolutely astounding when 96,000 words is a long novel. So you can see how 1 million of those is an incredible amount of context we can load in. Not only that, but it started to become cheaper. So Anthropic, Gemini, OpenAI all introduced ways to cache the tokens or cache the data that you put into the prompt. And hence, cache augmented generation was born, because actually we now have the opportunity to store the data in a cache that takes up a low amount of memory, and therefore only the tokens only have to be processed once for a set period of time, which makes it significantly quicker and easier than using something like RAG. And also you have access to all of the context now compared to when the models were initially introduced and you couldn't put this much context in. So let's go back and start building out a CAG agent inside N8N. And it's actually very straightforward. You just need to know how to do it. So there are different types of CAG. The one we're going to discuss today is prompt caching. So OpenAI and Anthropic use a technique called prompt caching, which effectively means it will cache a lot of the data automatically that's added into the prompt. So it actually makes it super straightforward to do in something like N8N, because if we structure the prompts in the right way, it's automatically going to be cached for us. So I've just gone to OpenAI's docs around prompt caching here, and it's got a few key things for us to note here. So caching is enabled automatically for prompts that are 1,024 tokens or longer. So it's actually quite a small minimum limit at which a point it would be cached. If we hit it with multiple queries, then how it works is it checks. The original prompt is passed in. The context is then cached. When we place another query with the same set prefix at the start of the prompt, it will say, okay, let's look up to see if that matches the data we've cached already. If a match is found, it will therefore use the cache response and feed that context into our prompt. And that will massively speed up the process of doing so. And that will massively speed up the process of retrieving that information, and as well as reduce costs, because we only have to pay a small additional fee rather than paying for all of the tokens again if we've included a bulk bit of context at the start. If there's a miss, i.e. the start of the prompt is not the same, then it's not going to detect it's the same. So when we're in N8N, what we'll do is we'll just create this Google Drive trigger again. And I've just re-uploaded the Netflix financial document again, so the 84-page document. Hopefully it's not above the token limit for OpenAI. We'll find out in a minute. And to make it more visible, I'm going to open the OpenAI node directly, and we're going to say message a model. And any return from the OpenAI node will actually tell us how many tokens of that initial response was cached. So we're just going to choose 40 mini. And the important thing here is every single time the prompt has got to be exactly the same. And we'll just give it a generic prompt here. Use the below documents to determine a relevant answer. Do not make information up. We'll pass through the document in here, and then we'll also pass through the user query, which is going to change every single time down here. So here we will actually have the user query. So what we're going to do, we're just going to swap this out for a chat trigger actually. And we've already got a chat trigger in the window, so we'll go and grab that from up here. We'll drag it down because actually what we're doing is downloading a specific file to feed in here as an example. So we'll add in our extract from PDF stage, and that will return the data. And then inside our OpenAI node here, we're going to just dynamically pass in the text that's retrieved from the document, which in this case is the financial document, but also the user query. So we'll pull dynamically the user query.item.json.chat input, I believe. And now if we try to open the chat and run this, we'll update this to a URL. We'll feed in the URL of the Netflix document here. And now let's try and run it just with a hello. It will now download the file, extract the contents, and hopefully feed that in dynamically to OpenAI. And let's just check the information was actually fed in. So we can see that the document's been fed in correctly because it's got all of this 84-page context. Let's scroll right down to the bottom. Chat input was hello, great. So actually we can look, and now let's try and ask it a question. So before we were asking about the Q, about the 2024 revenue streaming numbers. And we'll see the file will be downloaded, it will be extracted, it will be fed into OpenAI, and we'll be able to see in the response, one, if it comes back correctly. So you can see that's the exact same number we had earlier. It's added the 000 again by mistake. It must be something in the document that's causing that, but it's actually pulled all of the relevant information and it looks pretty accurate. Let's go into the logs. And if you just make sure that there's no simplify output here, we'll run that again. And if there's no simplify output, we can see exactly how many tokens have been cached. So 60544 out of 60818. So actually only 156 tokens, which is probably the question we asked, have not been cached. So most of that query we've not been charged for. And we've got a little table here to demonstrate the actual cost of reading that back. So like we said, 1024 are the minimum tokens to feed in here. There's no storage cost because it's actually storing it for around 5 to 10 minutes. So this is for very short use cases, but there is an additional read cost, but it's very, very small, 0.00375 per use. And we're getting a 50% discount on the tokens there. You can also use it through a generic AI node through OpenAI. However, you cannot see the logs of how many tokens were cached. So I wanted to just show you exactly how many tokens were cached here, so you can see. But now we could ask multiple questions and all of that is cached. So super easy to set up. If you want to do it through Anthropic or Claude 3.5 Sonnet, whatever, it's got the same minimum number of tokens, 1024. It's got an initial write cost, and again, a very low but slightly higher read cost per use. But the actual discount you get on a per use basis on the tokens is 90%. So say, for example, we had a cache of 10,000 tokens. We pay for it once to be uploaded and processed into the system. Then every time we read that cache, i.e. it confirms that we are trying to use that cache, we pay a read cost, a single per use read cost of this. of $0.015. But also all of the tokens that are read back, we pay effectively for those tokens again, but 10% of the price. So we get a discount of 90%. So we actually only pay for 1,000 tokens rather than the initial 10,000 in our example that we uploaded. So significantly cheaper. And you can see from our results here that it is much quicker to set up and easier to use than RAG. So the biggest difference with the prompt caching for Anthropic in particular is mainly in how we do it inside N8N. So within N8N's Anthropic node, we cannot actually use the caching function. So we need to connect to the API using a HTTP request. And inside the Anthropic docs, inside prompt caching, they give you a curl command for this request. So all you need to do is take everything inside the D here, take it back to a fresh HTTP node in N8N. We'll use the body type JSON, and then inside the JSON expression, we will paste in this. We can change the model to 3.5 Sonnet, whatever we want to do. But the one thing that's different here than a traditional request to the Claude model is that we've got this cache control type ephemeral, which just means that this text that we insert in here is going to be cached. So actually what we want to do there is pass in the full document. So let's turn this to an expression. It is an expression. So from the extract from file .item.json.text, that is the full text. And we just want to make sure that that is stringified, so it's not going to cause any errors. So we're going to just wrap that in json.stringify inside the brackets there. And that's just going to turn it to text. We'll remove the quotation marks so that we're not doubling up and causing a JSON error there. And then we are also passing in our user message. So instead of analyze the major themes of Pride and Prejudice, let's again pass in from the chat trigger .item.json.chat input. And I believe that should already be wrapped in quotations. If not, we need to wrap it just to make sure it doesn't cause any errors. So that is now wrapped. Inside the rest, we need to make sure it's a post request. We're sending to this URL here. You need to connect your API key through Anthropic, which is a predefined credential type. And you just insert your API key inside here. And then we need to make sure we've got the following headers: Anthropic version 2023-0601 and content type application/JSON. And if we now make sure it's connected to our extract file, make sure all other triggers are turned on. And now we're just going to ask about the revenue for streaming in 2024. And let's give that a run, see if it runs through Anthropic. And that's processing, and it's quite a lot of data, so it might take a little bit of time the first time it processes. But the next question we ask, it should be significantly quicker. And it's come back and it has given you the correct revenue, again with the zero mistake, but it's actually pulled back the correct revenue. If we go into the logs in here, we can see the number of cached input tokens, and the same applies again. Whenever we run a new user query through here, it should return a lot quicker. Give me a breakdown of revenue costs, and we're going to run that, and it should run significantly quicker this time. Okay, so we've actually reached our request limit because we just tried a second ago, so we just need to wait maybe a minute or so and rerun this. And I guess this is the danger also of using something like Anthropic through the prompt caching. You're also rate limited there. So if you've got a huge document like we've got here, 84, it worked through OpenAI quite well. We're being rate limited by Anthropic. It might be better off storing that in an updatable RAG and pulling it in a little bit at a time. But that being said, Claude 3.7 Sonnet has a high number of input tokens, but our plan only allows us to put 20,000 input tokens per minute. So that's where the problem is coming here. Because actually when we read back that data, it still gets input into the prompt. So we're exceeding our 20,000 limit. So back here, we've run this again and it ran fairly quickly. It's now come back with an answer of the different operating costs. So this does actually work. It just we got rate limited because we'd uploaded such a large context window. So with that being said, let's sum up exactly what we've learned here today and what we've built out. So first, we built out a basic RAG, and we realized that with a basic RAG, we couldn't pull things like table of contents because when we were splitting up the documents into chunks, we often lacked context that meant when we tried to retrieve it, those chunks weren't retrievable with the right semantics. So we then learned how to create contextual RAG through Anthropic's method of adding context to our RAG chunks. And that worked much, much better for accuracy of retrieving things where we had chunks separated over several or data separated over lots of chunks. However, we learned that actually with a traditional RAG setup, it works well with static data. But if you want to update it, you need to advance that. So what we did was we then went in and created a flow to update our RAG pipeline. So we did that by deleting the rows by deleting all chunks that were relevant to a document that had been updated by tracking it via its ID. We learned about metadata, but then we also learned the limitation of RAG itself is the slow or costly setup, and the fact that when you're retrieving, you have to go through an additional step to retrieve data from the vector database. That's when we introduced CAG, which is more relevant for smaller data sources, definitely, but more recent models that allow a higher token limit. And we learned how to do that in N8N, but we also learned that it was quite costly for large amounts of data. And it's also hard to update because we've got one set of data, and that set of data often expires very quickly. We didn't talk about a workaround for that, which is using Google Gemini, which is slightly more complex. But we then moved on to CAG for Anthropic, and we experienced, again, similar limitations to the OpenAI. Very easy to set up, but slightly harder because we can't do it directly through N8N. But that's when we stumbled upon things like rate limits, which meant actually for large data sets, maybe RAG was better after all. Well done if you've made it to this point. You've really ended up building out a lot. We've got our CAG pipelines here, our updating files, our adding context here, and then back to the start where we built out the basic example of a RAG, ingestion and retrieval. Feel free to check out the links to my community where I teach more of this stuff and have more in-depth topics like this, step by steps, teaching nearly 500 members how to use AI in their business, but also how you can build this stuff for other clients and make money using it as well. All of these templates are available in the school, so feel free to check it out. Thanks so much for watching.